scientist, and she works on large models for applications with health, and we look forward to this talk. Olivia is also a graduate from this department. She earned her first degree here and then went on to Oxford to earn her PhD. I'll not use more of the time, please.
Thank you for having me. So hi, I'm Olivia. I'm a research scientist at Google. And today I'm going to talk about some of our recent work in AI for healthcare, and in particular, how can we build trustworthy AI systems for healthcare. I'll first start with some context around where we can see medical research in this field going with new developments within AI. And then I will go on to some of the work that we've done that is trying to think about how we can enable trust and some of the technical solutions that we've been thinking about. Please do feel free to interrupt me at any point in this session. And I also want to thank my colleague, Ira, whose slides I have heavily borrowed from. So if we think about how to build an AI system in healthcare, we have a variety of different data sources that we could think about using. So for example, we can obviously use like patient representation, so imaging data, electronic health records. We can also think about using genomic data and pathology data. And that is just one source. We can also think about using things around established knowledge, so say data derived from textbooks. And we can also think about using more maybe elaborate data, such as 3D meshes in order to model parts of the body or brain networks. But when we are actually thinking about building these AI systems, we have to think carefully about how we store this data and how we input it into our system, especially if this original data could be sensitive. So for example, with electronic health records, we could have information about a patient's age, about their ethnicity, about their history, their medical history, etc. And we also have to be careful and cognizant about the limitations of the data that we're using. So if we have only selected our patients from a certain population, then they may have certain demographics. And so we have to be careful about the claims that we're making about how our model is going to generalize. But given all this different sources of data, it's quite an exciting moment as inspired from large language models, and how by combining all of these disparate data sources, we can unlock new capabilities and new experiences. I think there's a similar transformation that's happening in health AI research. So moving away from this kind of specialist data models and thinking about how we can create these generalist systems and where does that make sense and what kind of capabilities can we unlock. So there's been some interesting articles that have been thinking about this and kind of giving some interesting examples. So for example, you can think about segmentation, how maybe originally you would have built a model that is specific for a specific region of the body, but now maybe more modern methods would think about how can we build a kind of meta kind of solution where we take as input some examples of segmented parts of a certain type of the body, and then we get the model to predict, given a new example for that particular part of the body. But such a model is able to be applied in many different scenarios. And then maybe, we can go beyond that and try to think about a more generalist medical AI system that can be trained on multiple different medical modalities through different self-supervised techniques. And then maybe we can have these interesting interactions or benefits of being able to combine different modalities, and therefore be able to combine information across different modalities and have new capabilities. And so here we show three possible use cases, again, coming from that previous paper, that are quite interesting that you can imagine. So for example, you could have such an AI system that enables a kind of bedside interaction where it's able to monitor the patient and then kind of alert a physician that something is potentially problematic, and then the physician can respond and ask questions and understand what they need to do. You could also have again, a system that is able to create or help a radiologist expert by giving some report, but also actually grounding the information that's being generated in the actual image. So again, the expert can check the information, understand how these reports are being generated. And finally, you could have like even a kind of interactive situation where the medical AI assistant is maybe acting a bit more like a knowledge base, where a surgeon is operating and thinking and asking questions to it, and then getting some kind of response that's able to aid in their operation. And one such project that's being worked on at Google, which, disclaimer, I have no affiliation with, is this MedPalm work, which aims to see how we can leverage these vast amounts of different types of medical data in order to create a general model and then solve a variety of different tasks. But I think there's a lot of challenges with these types of work. How do you build the evaluation set? How do you ensure that you're really learning something new? How do you ensure that you're not letting information from your training set leak into your eval set? But it is a very exciting area of work, and maybe it gives the possibility of creating personalized healthcare. But actually integrating AI into healthcare, as I'm sure many people have experienced in this room, is actually very, very challenging, and it is very complex and fraught because there's a lot of issues that come in when you're dealing with real people in real situations. And so it is really important to really think about why are these approaches failing to actually be adopted. And this, I think, article has some interesting insights. But yeah, they have quite positive take. It's a journey that's worth undertaking because it promises quite an exciting future where we can have maybe more general healthcare, more personalized healthcare, etc. Within this talk, I will spend the majority of the time talking about robustness and fairness and kind of explaining why these two concepts are really important in the medical space and how we went about tackling it in our recent paper. And then I will also talk briefly about another paper that we did, which was on leveraging synthetic data for privacy and how that is also quite an interesting direction, potentially quite useful. So I think two very significant challenges within this kind of domain that arise when we deploy predictive algorithms arise from distribution shift and arise from issues around fairness. So issues around distribution shift arise when a model is deployed in new settings. So imagine that we take a model and we are training it. We've gathered data from one hospital or one domain, and then we deploy it in a new setting. Well, we can have different issues that arise due to label shift. We can also demographic shift. We can have shift in acquisition protocol. So for example, we could have different types of staining procedures, which I'll talk about for one of the data sets we looked at. We can also have shift in capture process. So if we're looking at, say, dermatology, we could have a user that is taking the image on themselves, or we could have a clinician. And maybe the clinician knows much better what kind of images are useful. And so we have that kind of distribution shift. At the same time, we can have these kind of performance gaps that arise due to fairness. So we could have simply by the population that we have gathered the data over, there may be differences in terms of the amount that we have from different subgroups of our population. And then this may also lead to unfair performance or imbalanced performance. And this is not a new thing. I think we all know that this exists in healthcare, and there's been quite a lot of work that has explored this in different scenarios. So this is one work that looked at fairness in terms of chest x-ray. And so what they found is that across different demographic groups, you get this varied performance. And in particular, certain groups, especially if you looked at the intersection of the groups, were performing much worse. So it is a really important problem because you don't want certain groups to be underserved by your model. And then another example would be this issue around age for dermatology, where again, because of how you gather the data, maybe you only have it for young people, and so it doesn't generalize so well to older, etc. And it can arise, I think, quite easily because if you're working with hospitals to gather data, then you may just naturally have a certain population, and so you may think it performs in a certain way, and then it doesn't generalize to a new hospital. And this is maybe quite an interesting way of categorizing the different reasons for why you may obtain this data set bias. So this paper is looking at the causal structures of data set bias and categorizing them into 3 different ways. And so what we have is we have this medical image, we have an annotation label, sensitive attribute, underlying condition, and a selection bias. And then what the image is showing is that the lighter version of the color versus darker denotes diseased or not diseased. And then the different colors denote different subgroups. And so ideally, we would have a classification line that obviously does not depend on the subgroups, but in reality, that does not happen. And the reason for that could be one of these three. So the first one would be prevalent. So in this case, the actual underlying condition is dependent on the sensitive attribute. And this could be either be a true dependency, or it could be because of selection bias. And I'll give some examples in the next slide of how this can arise. And then presentation is if how the disease actually looks or how it presents within the imaging data depends again on the sensitive attribute. And then annotation, similarly, but for annotation. And then these are some interesting concrete examples to kind of put this into context. And so, for example, for prevalence disparities, what we may have is, in a fair situation, we would have something that naturally happens. So, for example, patient's age would actually increase the risk of Alzheimer's, which would actually mean that there was more people who were presenting with the disease actually were older. Whereas something that maybe would be unfair is if we have a causal link between patient race and some kind of features, but the actual reason is that there may be different ability to access healthcare. So we may think it's more prevalent in one population, but in reality, it's not. And then similarly, you can think about this in terms of the presentation. So we could have the underlying attribute be the sex, and then that would actually impact, say, the breast density, which then can impact breast cancer. But in an unfair case, we would have maybe in different locations due to quality of care, maybe you would have different amounts of time to referral. So when they take the image, it would look different. And so again, you may think that there's this correlation, but it's not true, a true correlation. And so one thing that you might think is, well, why don't we just ensure fairness in the source domain? And this was something that was looked at by a colleague. And what they showed is that ensuring fairness in the source domain, i.e. the domain where you're training on, is not necessarily sufficient. So here what they showed was that if they, I think in this case it was dermatology, if they're training a model for dermatology and on their training set, they're getting a fair performance across different groups. That doesn't necessarily mean that in their held out test set that will generalize. And the reason for that is that you can have these kind of compound shifts where the sensitive attribute can be impacting many things, and you can't necessarily easily account for that. One thing that I suppose that we took, or that how we were thinking about this in this work, is that instead of worrying about it from the causal perspective, let's just try to focus on the experimental side and ensure that on the experimental side, we're trying to capture all of these different possibilities and try to evaluate our method across as many like distribution shifts or across the different subgroups in the actual test set. And that is kind of matches this idea that in order to actually make any claims about how useful your model is, you actually need to evaluate it in the setting that is actually going to be used. Because otherwise, for all the other reasons I mentioned, your conclusions may not generalize. Another challenge that is, again, inspired kind of some of our thinking around this work is that labeling data is obviously very expensive. But when we want to think about how do we actually evaluate our models on the different subgroups, and then we have that kind of combination of the expense of annotation, then the amount of annotation we may have for a given subgroup may be very small. And then if we want to use that for evaluation, then we're left with very little for training. And this is a paper that's kind of showing how that, how few images exist for different subgroups and annotation labels within some existing data sets. And you can see that for some sensitive attributes like ethnicity, there's very few annotations. So motivated by this kind of this background and this kind of extensive work, what we wanted to think about was how can we both make use of unlabeled data in order to improve our model, but also really take inspiration from all of those works that were saying that we really need to think about how we evaluate these models and ensure that we're evaluating them in different out of distribution contexts where we have all of these different kinds of distribution shift, and also in the fairness context as well. And in particular, we were thinking about how can we leverage generative models in order to create synthetic data and possibly make use of this unlabeled data in order to improve the medical classifiers. And our thought was that we could use these recent diffusion models in order to do so. And how we do this, and I'll talk about it in a bit more detail, but we use the labeled, weakly labeled, or unlabeled data to train the diffusion model. Then we take this diffusion model and then we can sample from it with whatever distribution that we care about. And then we can combine that with some real data in order to train our downstream classifier. And maybe I'll just mention, and one of the nice things is that because we can kind of change the sampling distribution, then we can use that in order to potentially make our model more fair and more robust. And the reason that we thought that this may work is that at the time, I think the paper was published recently, but the work started much longer ago. Jonathan Ho had come out with this very influential paper that was showing that actually image generation models were really getting really good. And so what we thought was maybe we can leverage these models. Let's see how good they are. And how they work is that at a very high level, you would have a data set of images, and then you will slowly noise them using some number of noising steps. And then you train a model in order to basically do the unnoising at each step. And then some of the properties of these that are maybe more important later in the talk, but that, for example, the more steps that you take, the higher quality the generated images, but the more expensive the noising process. And there was some, I think it was at the same time or like slightly earlier work that was looking at some of the public models for text image generation, so GLIDE. And they were looking at how good these models were for generating medical images. And they were surprisingly good. Like they did have some medical knowledge, but the authors did point out that they did have limited utility without proper fine-tuning and conditioning. But that was, again, a while ago, so I don't know what the current models would do on this kind of task now. But going back to our methodology, so how do we actually do this? So we proceed in the 3 steps, and in a bit more detail in the first step. In order to actually make use of the unlabeled data, we make use of something called classifier guidance. And we take the unlabeled data and we treat it as though it has a 0 label. And this is actually quite useful because it means that at generation time, we can steer the generations away from that 0 label. And that can potentially make our images more canonical, and so more canonical of the disease and potentially more useful. In the second step, how we actually sample the labels is that we sample the label distribution as is in the training set. The reason for this is that the prevalence of the disease may be truly indicative, and we don't necessarily want to change that. But then we can sample the property label as many times as we want. And so this gives us the ability to generate lots of additional data that we can then use to combine with our real data. And for that combination, we just treat it as a hyperparameter, which we choose based on our validation set. We apply this approach to settings of varying degrees of complexity. So we started with histopathology. So this, the task is to predict tumorous or non-tumorous cells. And the interesting thing with this task is that different hospitals have different staining procedures. So it might seem quite simple, the differences, but it does mean that you don't necessarily generalize very easily from one hospital to the next if you've only trained on one type of staining procedure. And obviously some people have looked at color augmentation, different types of things, which we will compare to. The second, more complex, is radiology. Again, this is a public well-studied data set, and here we have this demographic shift. And we were using 2 different data sets, which again may have like different imaging or capture processes. And then the final, by far the most complex data set that we explored was this dermatology data set. So we had a private data set from 3 different domains, very different, you can see with the images, very different capture processes, angles, etc. And also has both demographic and prevalent shift. It's also high resolution. And before I kind of go into the quantitative results here, the different images. So what you can see is that generations are actually quite high quality. So I think at the time, this was quite cool. I think nowadays you'd expect it. And they also reflect the characteristics of the conditioning label, but I'll give more examples for each one later on. So for histopathology, going into a bit more detail on the experimental setup, you can see the train and the validation set, and you can kind of see quite clearly, I think, the different staining procedures, and so how you have to generalize between the two. In this case, we had quite a lot of unlabeled data, but we only have it from 3 of the hospitals, and we only have training data from 3 of the hospitals. So the aim here is to learn something that generalizes to the unseen hospitals. So we trained the generative model on the unlabeled and the training labeled data, and then we evaluate on the in-distribution validation and the out-of-distribution data sets. And then here, the generated data, so I think it's quite clear. You can see the difference between the no tumor and the tumorous slide. But the question is whether these features that your classifier is going to learn are actually useful. And so here we show the results. And one thing to note is that we looked at this kind of more skewed and less skewed setting. And the reason for this is that we didn't want to just run an experiment once, but we wanted to see how robust were the methods if we really make the distribution shift more and more extreme. So in this case, we're kind of removing images from 2 of the hospitals in the labeled setting and making that an extremely small number, and then seeing whether we're still getting like performance improvements. And then in terms of evaluation, we evaluate both the accuracy and the fairness gap. And what we plot is how much we improve accuracy over our baseline, where the baseline is using no augmentation, and how much we improve fairness. And what we can see is that by using both the generation and augmentation, we improve consistently. So the baseline is just a standard ResNet training. And then we can do color augmentation, which is kind of the standard approach in this data set. We can add label conditioning, which is where we condition our generative model on just tumor or not tumor. We can add the property, which would be the hospital label. And then we can combine the color augmentation and the synthetic data generation. And what we can see is that, as I was saying, we can improve on these settings. But that was kind of the easiest data set. So now we want to see whether we can improve in a more complex data set. So the second one that we looked at is chest radiology. And in here, we don't have any unlabeled data, but the challenge is that we have 2 different data sets, one that we're using for training and one for evaluation. And they have different label distributions. They also have different demographic distributions, which I'm not showing here. And one of the interesting things about this data set is that you can have the conditions co-occur. So it's not that a patient just has one condition, they can have multiple. And so here are some generated images. And what is interesting is that the generated images are matching properties of the condition. So for example, for consolidated lung, the right lower lobe is too white. And that's because the air is replaced with something else, such as blood. In cardiomyogaly, we have this high cardiothoracic ratio. And for pleural effusion, we have some fluid buildup. And for pulmonary edema, we have excessive liquid accumulation in the tissue. So again, this kind of implies maybe our synthetic samples are learning something useful visually, but let's check it quantitatively. And so again, the plots are the same. We have a measure of fairness. We have a measure of accuracy or performance. Here we use area under the curve. And then again, we have different baselines. So here we use a pre-trained baseline on different data sets, different augmentations, and then our method as well. And we can see that again, it improves. And finally, we looked at this dermatology data set. And this was quite an interesting data set. So we have 3 different ones. So we have the training one and then 2 held out. And what's interesting is that for one of the held out, It's quite similar to our training one, but for the other one, the label distribution is completely different. And they're all acquired from different places. So for one of them is from the US, Hawaii and California. One of them is from Australia, and the third is from Colombia. So not shown here, but again, as you would expect, then we would get different ethnic and other types of population shift. We can also see that the distribution is highly skewed. So even if we weren't thinking about the average distribution, it still can be a somewhat challenging training problem, because if we're not careful, we'll just end up predicting the most common label and then we'll seemingly have great performance, but in reality it's completely useless. And then one thing to note is the high risk conditions, because in our evaluation, we focus on whether we are predicting these accurately, because if you in practice, if you were to miss something that's high risk, that's much more problematic than missing something low risk. So we try to use a metric that's maybe more realistic and useful than just pure accuracy. Again, let's look at some of the generative results. So I'm not a dermatology expert, but they seem, again, pretty reasonable. So things that are about the hair, you're getting like the scalp, and things that are like melanoma, you can see something that could be, from a non-expert point of view, look reasonable. And again, the plots are very similar to many of these now. So again, as with Chameleon, because we have less control over the data set, it was quite small. We again had this notion of trying to skew the data set to make it more or less biased in order to kind of look at how robust our model was in a variety of conditions. So the top is showing less skewed, bottom is more skewed, and then again, we have the fairness gap versus, in this case, high risk sensitivity. And again, we get improvements over the baseline, where the baselines are kind of looking at pre-training or different kinds of standard losses or approaches to handle when you have non-uniform labels. So we seem to get good results, and I think that we were a bit surprised, but we spent quite a lot of time trying to understand maybe why this was working. And I'm not going to go through all of these, but some of the things that we hypothesized is maybe why these synthetic images were useful is that they're diverse, they're realistic, canonical, they help to align the feature distributions between in distribution and out of distribution, and they maybe help reduce various correlations because the model has to be robust to all of these different types of augmentation. And one other thing that we did was we looked at a toy example to kind of validate some of our intuitions. So our hypothesis was that the synthetic data could be useful for two reasons. So one, it could help with better density estimation, and the second, it could help with compositionality. So compositionality would be where you maybe have an example in one subpopulation of a condition, but you have examples of another subpopulation the model is able to predict. That may or may not be true because obviously diseases can present differently. So that's not something that we were easily able to test, but potentially is something the model is able to do, maybe able to compose across different body parts or things like that. But one thing that we looked at was the density estimation. So here, what I'm showing this toy example is a very simple setup. So we have a 3-mixture Gaussian mixture model. And then what I'm doing is the big points in the simulation are labeled. And then the small points are the unlabeled data. And then we're doing a simple clustering algorithm in order to fit it. And as you can see that with very few labeled, but many unlabeled, we're actually getting quite close to the true mixture. And we actually did run, like, again, this very toy setup where then we train classifiers on this, and it does seem to improve performance in some cases, in certain conditions. But that seemed to validate our intuition. And the other thing that we did is that we took the dermatology synthetic images and we validated with dermatologists that the images we were generating were realistic and useful. And so what we did is that we first asked the dermatologists if these images were of sufficient quality to annotate. And that was true for about 50% of them, which again was again, at the time, this was quite impressive that you could generate images of people and it or parts, very close-ups of parts of the body, and they were realistic. And then for the ones that they could annotate, then we looked at the accuracy in terms of what the dermatologist predicted and what the true diagnosis was, and then a confidence level out of 5. And so what was interesting was that they were very confident, and actually the accuracy was quite high. And then we looked at different baselines to see how good this was. So the second row is if we had 100 dermatologists on the same conditions. And basically what we do is we hold out one dermatologist and we look at their performance in comparison to everyone else. And the final one is a different paper that had looked at a similar kind of thing. Again, how reliable or how accurate are dermatologists. I think in that case, they compared to experts. And you can see that it's actually not that far off, which again was quite promising. And one disclaimer is that these synthetic images are just used for training. They're not used to train a person or anything. And another thing maybe to mention is that even though 50% are maybe not deemed of sufficient quality to annotate, it doesn't necessarily mean that they're not useful, because they could still be helping the model to learn useful features.
I've got a question.
Yeah.
I'm curious about the compositionality. Do you validate those aspects with dermatologists? That's
an interesting point. We didn't do the compositionality because I suppose that is something that the generative model could learn without any labels. So then the question would be, how do we validate that? Yeah. So the closest thing that we looked at was I don't have slides for it, but was the canonical question. So in that, what we did is we generated for different diseases, we generated images with the model, and then we looked at the nearest neighbor as well as if there existed, the canonical images in the data set. Because I didn't really go into it, but in the data set, we got multiple dermatologists to annotate. So we have some kind of notion of how confident that group is in the image. Yeah. And then visually we can compare. And it didn't seem that it was kind of collapsing to the nearest neighbor. It seemed that it was learning these kind of canonical images. But that is a very qualitative analysis. I think actually doing that in a quantitative way is quite challenging, but quite an interesting question.
Sure, it's just that with the table that you showed after, I was curious of whether you'd split the synthetic images and kind of showcase whether it's lying in between two different groups, like from the previous slides. So where the model thinks it is in all those samples.
I'm not sure what you mean.
So if you take disease A and disease B, your model could somehow fill in the gap between.
Oh, I see what you mean.
And so where does it think it lies between? And then you just hold those out and see what dermatologists say about those samples. So then you get an idea of how they kind of rank these.
Yeah, that's interesting. That is not something that we looked at. In my mind, compositionality would be like composing, say, different body parts with a disease that hasn't seen before. But that's interesting. That's not something I looked at. Any other questions? In terms of limitations, we did spend quite a bit of time in the paper trying to just go through some of the limitations of the model, because I think it's important to be very conscientious in this line of work. So the first thing is that coverage of missing regions. Obviously, with the generative model, we can't imagine what's not there. So if we're missing some kind of subgroup of population, or if we're missing some diseases, we'd need to collect more data. The second is that we were very conscious to only use generated data as augmentation, not as evaluation data. Third is, this is more technical, but handling the large image sizes was quite a bit of a pain because we had to train upsamplers and stuff. Maybe this would be easier with more modern methods. And then actually doing some of the selection of choosing the best model could be quite a slow iterative process because then we had to train the downstream classifier. And And also, I think one thing that we really took from this work is that doing the evaluation was not necessarily challenging, but it was something that we had to be quite thoughtful about because we were very constrained by the data sets that we had. And so how could we make best use of them in order to try to really robustly evaluate our method? And so that's why we thought about this like skewing of the different data sets, trying to use multiple different ones, different types of shift, etc. And then I will briefly kind of go through some of this work on privacy, which I hear some of you are interested in. So I'm glad that I had these slides. And I think it's quite an interesting area because it could make some things around like an AI, ML application in healthcare a lot easier. Because if your synthetic data was completely private, then you could maybe share it more widely and not have to worry. Once it's made, then you could share it and you could reuse it for multiple applications, and it could make some more maybe larger system aspects easier. So what we were inspired by was differential privacy. So differential privacy is a method for training models that allows you to have a quantifiable privacy budget. And so basically what it says is that each training point that we have can only impact the model so much, and that so much is quantified by your epsilon or your privacy budget. And so if you have a really low budget, then you're not going to leak any information from your training set. But also what it typically means is that the performance of your model is so bad as to be completely useless. And so here are some examples from previous work. So you have to make your, say, epsilon budget massive, 10 to the 15, for it to give you anything that doesn't resemble noise. And so what we were looking at is, can we take these diffusion models and actually train a model with a reasonable epsilon budget that is useful? And one of the inspirations for why we thought that was possible is that these models are actually quite simple to train because you're just doing an MSE loss on different pairs. And one of the tricks to get differential privacy to work is to do lots of augmentation. And so you can think of each time step that you sample from, each noise seed that you select as an augmentation. And then that is very beneficial for differential privacy. If you want to know more about why that's the case, happy to take questions. But then some of the insights that we have for why, for what we could do in order to best leverage these diffusion models was, for example, that if we look at the time step and we look at the amount of data that is, amount of information that is leaked, we can see that information is leaked not at the end, not quite at the beginning, but in the middle. And so those are the places that we really need to ensure that we really need to sample from in order to train our model. So we don't necessarily want to focus on the easy parts that are later on. And also some other things that we thought about was, again, the augmentation and pre-trained models. Those were some of the tricks that we used. But using that, we were able to generate these samples. So on the top is real samples, on the bottom is synthetic samples. The images are quite small, but I think you can see that actually they're quite reasonable. So potentially they're quite useful. And indeed, if we look at the performance on, say, Cypher 10 in terms of FID, so a measure of quality, then we're doing significantly better than the most comparable methods within a similar epsilon budget. So the epsilon budget is along the x-axis, and you can see that, instead of it being 10 to the 15, they're quite reasonable, like 5, 10, 32. And then on the y-axis, FID. And if you don't use this, I think the best models are around 2 or 3 in terms of FID. So not as good, but not terribly far off. And the other thing that we checked was, if we then use these images for training a downstream classifier, how well do we do? And again, we're getting quite high performance, so almost 90%. I mean, obviously, if you train the model, you can get even higher, but it's quite promising. And then the next thing that we thought about is that what would be like potential use cases for this kind of approach, so using differential privacy in order to create these private synthetic samples. And so one thing that you could do is that you could use the generated data repeatedly for training a range of different prediction models and then choosing the best one across them. And so the reason for this is that if we were to train with DP on the real data, then each time we train, then that would cost some kind of budget. So instead of we can use synthetic data in order to train our model, choose hyperparameters, then we can do much better with much less cost. And so here, what we're showing is that if we train on synthetic data and then evaluate it on real data, that we actually generalize. So you could imagine like training a model on synthetic data, putting it out there, and then having someone else use it on real data. And a different thing that we could think about is that you could have like a third-party person who actually goes and uses the hyperparameters that you chose from the synthetic data. And so you can see that the hyperparameters are kind of do correlate across the synthetic and the real examples. So that is to conclude the differential privacy part. Again, are there any questions on that part? And then I thought I'd just conclude with some thoughts. So I started this talk by discussing AI agents and how there's potential paradigm shift. And so I thought, before I go into that, but I thought one thing that we could think about is why is synthetic data so useful? So for example, one thing is that we can reuse this data, and especially if it's private, we can potentially reuse it in sensitive situations. Another nice thing is that it's quite scalable. So if we have a perfect generative model, then we could imagine that this would scale very well. And then, yeah, so if we could actually combine these different methods, then you could imagine being able to leverage private data sources and be able to build even better, but also trustworthy models. But taking a step back, so I spoke about two different kind of technical approaches to looking at robustness and privacy, but there are a lot of other considerations when building these kinds of models. And there's a lot of organizations also thinking about what are those principles, what should they be, how should we go about doing this? And this is becoming especially true as more and more AI models are being used out there. It's becoming more and more prevalent in wider discussion. And I think it's quite an interesting thing to think about from a technical perspective. What kinds of solutions can we create that enable these kinds of goals? And also from a technical perspective to think and work with socio-technical people to think about what are the missing evaluations, what are the missing tools that are needed to achieve these kinds of trustworthy AI models. But I'll finally briefly mention other stuff that we've been doing. So this is not related to the health side of things, but is related to maybe the more trustworthy side of things. So we've been thinking about in the large model space, how do we think about fairness? How do we think about alignment? And then also on the provenance side, how do we think about creating tools for increasing trust in information? But that is it. So thank you for listening. And obviously, thank you.
There to tell the online audience that if they want to ask questions, they can put them in the chat and I will read them aloud. In the meanwhile, perhaps we can ask this audience if they have general questions that can be asked. Any questions? Any question?
Thank you very much, Olivia. This was a great talk and very good methods. Can I ask, I very much liked the idea of generating canonical examples, canonical synthetic examples, so very prototypical of one particular label. However, since, especially in evaluation, since real data are often noisy in the labels and noisy and so on, is it possible that this could promote some kind of overconfidence in the predictions? And did you notice somehow something like that? Did you mitigate it?
Yeah, that's a good point. I think in this case, what we were worried about was that because they were user captured, that a user would be like photographing the completely wrong side of their body. So the thing about the canonical was just validating that the features the models were learning made sense. But I think that's definitely true that if they are too canonical, then it may not generalize. But I suppose that goes to the point around ensuring that your evaluation is not too close to your training distribution, that actually you've learned these very spurious correlations that don't generalize. And so in the dermatology case, the imaging protocols for some of them were completely different. I think they used different cameras. So the fact it was able to generalize gives me hope that it wasn't just learning those spurious correlations. But yeah, I think having to rely, you have to, in my mind, that's where the evaluation is key to ensure that.
I'm thinking about this from a longitudinal health monitoring perspective, where I think a lot of the samples that you get, it's most often than not, it's people going into a clinic after they've observed some form of discomfort, and so they get a scan done. So it's almost off the stage where the disease has progressed, and there's the healthy stage here, but there's all of this gap in between where there's no data collected. And so I was just wondering how this sort of synthetic data generation model might be able to fill that gap such that if you pick data points at any given point in time, if that makes sense, then you'll be able to tell which stage the disease is in.
That's really interesting. I think you could do something there, because if you had data where you knew, like, so say you had like, this is healthy, so 0-month diagnosis, and then you had like 1 month, 2 month, 3 month, you could use that as a label to your generative model, and then you could vary that axis if you made it continuous. And I think that could be really interesting. Yeah, we didn't have data for that, but that's really interesting.
My question was more, you said you've done this work quite a while back and you used these fusion models. I wonder if something in the methodology would change if you were to do this now.
I think diffusion models are still the best, but I think the ways of training them have gotten better. So for example, the architectures that people use have changed. So we use like the UNet, whereas now people use transformers in the middle. The way that we did the upsampling, which was a pain, because we did a 2-stage approach, I think that would not be necessary anymore because you can do like progressive growing. So I think actually the methodology would have been easier in some ways if we did it now.
Interesting. Okay, I don't see any questions online. I don't see any questions here. So all is left is thank you very much again.